Hello and welcome back to MathsBytes and video 10 of the binary number series. This video is still about converting decimal numbers to binary using the halving division method. We will start the video by recapping how to convert a decimal number to binary using the division halving method by doing an example. We will also discuss how to check your answers and workings, and in the final part of the video we will come up with our own step-by-step instructions for the division halving method for decimal to binary conversion. I hope you will learn something useful from this video. So, let us get started by reviewing how to convert decimal numbers to binary using the division method. I would like you to pause the video here and convert 75 using the division method. Here is the answer. 75 in decimal is equal to 100111 in binary. Did you get it right? I hope so, but if not, can you go through your table and try to spot your mistake? Now, in the previous video, I already mentioned that we can check if our answer is correct by converting the binary answer back to decimal and see if we get the same number back that we wanted to convert, in this case 75. Let us just do that. Placing the binary place values on top of our binary number, we get 1, 2, 4, 8, 16, 32 and 64. Out of these place values, we used 1 plus 2 plus 8 plus 64. 2 add 8 makes 10, add 64 makes 74, add 1 makes 75. So our answer is correct. This quick calculation worth doing in the exam. By checking your answer, you will achieve two things. 1. You will have a chance to make corrections should you have made a mistake, which can happen easily under stressful exam conditions. And second, by knowing you got the right answer, you will be able to calm your nerves a little. If you are not learning about binary numbers for an exam, getting into the habit of checking your answers will still serve you greatly. Once you are out in the big wide world of work, often you will only find out you made a big mistake when it is too late if you are not in the habit of checking your answers. It is not a coincidence that unit testing is so widely spread in coding circles. The earlier you start building the habit of checking your work, the better, at least in my opinion. Now I would like us to spend some time thinking about how we could identify where our process went wrong should we end up with an incorrect answer to a conversion. It might not be the most important thing to find where we went wrong with this specific process, but as a programmer, you will spend a lot of time debugging, and getting used to identifying ways to check processes will help you become better at spotting bugs in codes. To be able to do this, I would like us to spend some time first on observing the properties of the field decimal and binary conversion table. Let us do this through another example. Here is how I would convert 123 from decimal to binary. What can you spot when looking at the individual rows in the table? Well, in each row, the decimal column is the sum of the even and remainder columns. For example, 123 is equal to 122 plus 1, or 30 is equal to 30 plus 0. Also, in the even column, we should only have even numbers. The number in any decimal column, except the first row, is always half of the number in the even column one row above. For example, 15 is half of 30, and 3 is half of 6. The last column only has 1 or 0 in it, and finally, the last row is always 1, 0, 1. So if we know these properties of the table, we can check any table and see if there was a mistake made somewhere. For example, here is a conversion. Is this correct? And if not, where is the mistake? First, we want to check whether the conversion is correct or not, so we quickly convert the binary back to decimal. The place values are 1, 2, 4, 8, 16, 32, 64, 128 and 256. Out of these, we used 256 plus 128 plus 16 plus 8 plus 4 plus 1. 256 add 4 makes 260. Add 128 makes 388. We can add 16 in two stages. First adding 10 will make 398, then adding 6 will make 404. We still have to add 8 and 1, so we can add 9 to 404, which is 413 and not 405. So there is a mistake somewhere in the conversion process. The mistake is in the row of 50, 51, as 50 add 1 makes 51, not 50. This is also an easy mistake to fix. We just have to swap the 1 in the remainder column to 0, as all the other rows in the table are correct. Now, our new answer is 1100100101. And let us make sure this is the binary equivalent of 405. The place values again are 1, 2, 4, 8, 16, 32, 64, 128 and 256. But this time we only have to add up 256 plus 128 plus 16 plus 4 plus 1. So 256 and 4 is 260. Add 128 is 388. To add 16, we can first add 10, which makes 398, and then add 6, which makes 404. Then lastly, we add 1, so the answer is indeed 405. Also, we took out the place value 8 when correcting the table, and indeed, the difference between 413 and 405 is 8. So we are all good now. I hope you appreciate having a go-to method of checking your own answer, and if it is wrong, being able to identify and rectify the mistake without having to wait for someone telling you if you are right or wrong. This one skill is pretty valuable in the workplace, in my experience. Here are 3 more conversions. Can you spot the mistakes in them, if any? Pause the video here and try this exercise. And here are the mistakes in each. The first table, 59, has a mistake in the second to last row. The remainder is incorrectly recorded as 0 instead of 1. So the right binary answer is 59 in decimal is equal to 111011 in binary. The second table, 172, has a mistake in the fourth row from the top. There is an odd number in the even column. However, this mistake didn't make the final answer incorrect. In programming, these mistakes are a kind of stat mistakes, the one that are not obvious and don't seem to make a difference to the final answer, but are indicator that something is not quite right with the code, and in the next upgrade, all hell could break loose, because this is an indicator that something is not fully understood from the process. So make sure, if you find these kind of mistakes, you fix them right away. The last table, 29, has no mistakes in the table, but the REM column is incorrectly copied from top down instead of bottom up. So the final answer is incorrect. The correct answer is 29 in decimal is equal to 11101 in binary. This is probably the most annoying mistake of them all. After all that hard work, messing up with the last step can be quite disappointing. Make sure you look out for the type of mistakes we just found in the exercises and that your table won't have them in your exam or assignments. I would like us to spend the last part of this video on coming up with our own step-by-step instructions algorithm for converting a decimal number to binary with this division method. Again, I will ask you to pause the video here and take this opportunity to practice. Being able to come up with precise algorithms that other people can follow is almost an art that takes some time to develop, but is really beneficial in the field of computing and programming. Again, pause the video here and have a go at writing down this algorithm. Again, write this down and don't just think about it to avoid confirmation bias. Here is one way we can write down this process. Now, I appreciate that so far this is our hardest procedure, for which we had to come up with some sound instructions, as quite a few things go on in many of the steps. So if you found this a challenge, rest assured, most people will find it a challenge. If you didn't find it too hard, then a massive congratulations. You are a natural at thinking about algorithms, so you probably will enjoy becoming a programmer very much. However, having a go at this exercise was almost more important than getting it right. By having to think about this conversion, you allowed yourself to make deeper connections between the concepts involved, and in return, you build a better understanding of the whole process. I strongly believe that if you try this way of thinking about any processes, you have to learn whether it is a maths problem, or else you will quickly build up a better, deeper understanding of the subject and its method processes. Now it is time to review what we covered. So, in the first part of the video, we have converted a decimal number to binary using the halving or division method. We did this so we are all reminded of the process. Then we looked at the properties of this method, especially how the table is filled, and used these to identify how we can check if our answers to these conversions are right. We can check if our final answer is right by quickly converting the binary number back to decimal. Then, looking at the division table, we observed that in each row of the division table, the numbers in columns even and remainder has to sum up to the numbers in the decimal column. Also, in the even column, we can only have even numbers. The remainder column can only have 1 or 0. And finally, the numbers in the DEC column, save for the very first, are always the half of the number in the even column from the row above. Then I gave you 3 conversion tables where you had to find the mistakes. I hope you took this opportunity to be a kind of detective and find the evidence of wrongdoing. In the last section of the video, we did probably the most important part of this video. That is, we created a 6 steps instruction for carrying out the decimal to binary conversion using the new division halving method we introduced in the last video. I hope you start to see the value in us trying our hands at and sometimes failing at these step-by-step instructions. I strongly believe having the skill of being able to break down a process into smaller, more manageable steps is a vital skill for any computer scientist, especially for those who aspire to be great coders. In the next video, we will move on to look at how we can add decimal numbers, so we have something to build upon when we look into binary addition in subsequent videos. Until then, keep learning, one byte at a time.